time immemorial. We hope that this presentation can help you learn more about the science of the Wolastoq, while we understand that there is much more cultural and spiritual learning for us to do to better understand and appreciate the waters we know as the Wolastoq. And now I will pass it off to Dr. Shalaby.
Good afternoon, everyone. I'm pleased to be invited to the second webinar for maritime climate modeling and upper Wolastoq River water assessment and best practice. In this lecture, we will delve inside the climate models world to have a fundamental understanding of the model structure and have an overview of their possible application. What is the atmospheric model? What is the
Dr. Shalaby, excuse me.
Yeah.
If you could click take control, you can go through the slide deck.
Sorry.
No problem.
Now.
There we go. Thanks.
Okay. So to start with, what is the atmospheric model? What is the difference between weather model and the climate model? It is any model that represents some or all the physical processes in the atmosphere, land and ocean, and the mutual interaction between them. Have a few seconds to look at this picture. This picture illustrates the basic building blocks of any atmospheric model. The main large systems are the atmosphere that contains solar energy, upper wind, and the clouds. The second system is the land surface, snow and ice, forest, lakes, and the human. The third large system is the ocean that contains surface wind, internal ocean current, and ocean salinity and temperature. These components are the building blocks of any atmospheric model, and they interact directly and indirectly. This interaction shows itself, for example, in the hydrological cycle at the global and regional scales. It manifests itself in forest fire, for example, in a seasonal cycle, forest fire seasonal cycle. If you want to have a closer look of one of a complex interaction, let us examine the complexity of atmospheric chemistry. How long does, for example, the halocarbons last in the atmosphere? Why do we have ozone depletion or so-called ozone hole in the southern hemisphere rather than the northern hemisphere? Thousands of chemical compounds and aerosols emitted in the atmosphere, whether by human activity from industrial and agricultural activities or naturally from plants, animals, and wildfire. Ocean emits a complex of chemical compounds and aerosols. All of these chemical soup interact and they change within the atmosphere in milliseconds or in a century. Halocarbons last in the atmosphere for more than 100 years. It circulates the globe in 1 week and they stay up there waiting for the right condition to deplete our UV shield. This is nice, but how can we model all of this? Atmospheric modeler writes the model in a way such that it must conserve energy, momentum, and mass. Let us look at an example. The solar energy component is always the starting building block of any atmospheric model. Yet it is very complicated in reality, but atmospheric model does a lot of approximation. Here in this picture, you will notice that the solar energy input is equal to energy output, despite all changes inside the atmosphere and the land. The energy input is 341 watt per meter square, what is called the solar constant, and the energy output is 341 watt per meter square. Actually, 341 is the summation of the outgoing long wave radiation and the reflected or the outgoing short wave radiation. What are the approximation in this diagram? What do you think? Most of energy input is in short wave, visible light band. This is big approximation. We neglect UV, for instance, in this diagram. No differentiation among long wave radiation, where different greenhouse gas absorb and emits at different bands. We just consider just long wave as one frequency or one wavelength. This kind of approximation are considered for early atmospheric models. But again, how does the model predict or simulate the physics and the chemistry of the atmosphere and ocean? The answer is the Navier-Stokes equation. Navier-Stokes equations are the mathematical formulation of conservation of momentum, mass, and energy. The basic variables are needed to solve these equations and to predict the weather after 24 hours, for example, are very simple. You need to know the wind field in 3 dimensions, U component, V, and W. You need to know pressure, temperature, and water vapor. All these fields in 3 dimensions. Now, you have to know it right now to predict the next 24 hours and cover the globe from the surface to 50 kilometers up, which seems a very simple task to achieve. Consider you have this huge amount of data. How would you solve this equation? You need first to dissect the atmosphere or ocean into cubes. We dissect the atmosphere horizontally and vertically. We can increase the number of pixels as much as we want to resolve more features in the atmosphere, or land, or ocean. But this depends on what is your scope and your computational power, of course. Let us back to the question. What is the difference between the climate model and the weather model? To answer this question, we need to look at the atmospheric processes, temporal and spatial scales. But I forgot to tell you that after dissecting the whole space, we need to apply a very sophisticated numerical method to solve these differential equations. And this is another story. The first glimpse we got from this figure is that larger atmospheric phenomena occur over long time. Tornado has a scale less than 100 meters of influence, so it lasts for less than 1 hour. Hit, run, disappear. If you are so lucky, face the hurricane with a spatial scale less than 10 kilometers and last for a few hours. On the other side of the spectrum is the global warming phenomenon. It took more than 30 years to realize its global impact. There are fast atmospheric processes need to be predicted, and we don't care about slower processes. So in one hand, the weather model doesn't include slow processes like ocean current or sea ice seasonal cycle, but invest too much in cloud convection processes. This would simplify the weather model in some aspects. On the other hand, climate model includes these slow processes, but neglect detailed cloud convection processes to some extent, of course. So there is no atmospheric model for all scale, although big atmospheric centers invest in this direction. This schematic shows the acronyms for many scale-dependent models. The most expensive or computationally demanded model is the DNS. No one will using DNS. because it is in a centimeter scale or less for weather forecasts, not to mention climate simulation. What is relevant to our talking is RCM, Regional Climate Model, which stands for Regional Climate Model, and GCM, which stands for Global Climate Model. And you can see that GCM had the largest spatial scale and lowest resolution. Again, very few atmospheric centers afford to run GCM under 1 kilometer resolution. However, there is, of course, but they're very, very few. The history of climate models development shows the development of understanding the complexity of Earth climate system and how different science disciplines merge together to have better understanding of this system. You can see from decade to decade, different components from this complex system be integrated within the model itself. And now, right now, we have a very comprehensive models, which now we call Earth system model. We don't call it atmospheric or atmosphere oceanic model. It become Earth system model. The development also goes in parallel with ever-increasing computational power. As we start by ENIAC, which hosts the first ever 24 hours numerical weather forecast, and headed toward Oak Ridge National Laboratory, with Jaguar supercomputers. But this is in 2009. Now, after more than 10 years, we went to very high speed. The original climate model technically is called dynamical downscaling. It relies on information coming from a global climate model. The RCM resolve surface phenomena that are not seen by the GCM. This is the power of this tool. It is computationally efficient, needs low storage, easy to handle on desktop PC, easy to perform numerical experiments. You can simulate any region over the globe. In the following, I will show many applications of the regional climate model. RCM is one of the well-known regional climate model. It is developed in the International Center for Theoretical Physics, Trieste, Italy. RCM user can set the location, the extension, and the resolution of the required domain. And this simulation is 50 kilometer resolution. You can notice the Great Lake surface temperature, which is cooler than the surrounding land. This feature cannot be seen usually in low resolution global climate models. The precipitation patterns over Western North America is influenced by Rocky Mountains. Here in this simulation, we can see the effect of mountain to produce rain. Look at the northeastern British Columbia, where there is emergence of precipitation. But don't confuse between the large scale one and very localized pattern emerged nearby the mountain. Back to New Brunswick. This simulation is 5 kilometer resolution. It is clear how the model captured the small feature of northern New Brunswick, where the temperature field is differentiated along the Notre Dame mountain range. More closer look at, and you will notice the difference in temperature between the Grand Lake and the surrounding land at sometimes during the day. On the right side, this is the mix between large scale precipitation and convective scale precipitation. You can notice again the local convective precipitation band aligned with northern mountain range. If you compare this simulation with Canadian global model, you will appreciate the importance of the regional climate model in resolving fine surface texture. RICCM not only simulate wind, temperature, and precipitation, but also aerosols and gases. In December 2019, at Menton, Northern Fredericton, an accident results in a fire in tire recycling plant. The plume of the fire lasts for a few hours. The RICCM simulation shows some interesting features, such as the plume reached Nova Scotia within few hours, but more interestingly, the plume changes direction with wind abruptly. This tool is so important for Air Pollution Advisory Committee. RICCM has a comprehensive chemistry package that could predict many air pollutant species, such as surface ozone, sulfate, nitrous oxide, carbon monoxide. These examples show original scale simulation for a daily scale. What about continental scale and climate change scale? This simulation is a continental scale simulation using 50-kilometer resolution over Africa, and it shows the plume from seasonal forest fire in tropical forests in Africa. Finally, we come to the continental scale climate change simulation, and this show mid-21st century simulation for precipitation for different seasons, and how RICCM could simulate a very wide range of climate zones from Central Africa to Central Europe. The main message of this talk is to encourage students to use RCM and researchers to use RCM to conduct fairly complex numerical simulation in different research areas as forestry, hydrology, climate change, impact, land surface atmosphere interactions, and atmospheric chemistry. And thank you for listening. I'm ready for question. Thank you.
All right. Thank you, Dr. Shalaby. We're going to ask that we hold questions until the end. So make sure you've got them written down or you remember what you want to ask, and we'll have those put in the chat. We'll read them out after Dr. Qi presents. So Dr. Qi, when you're ready, click take control and take it away. Thanks.
Sure. Okay. Hello, everyone. Good afternoon. It's my pleasure to participate in this webinar series again. For those who did not attend the last webinar, my name is Junyu Qi, and I'm a research scientist at the University of Maryland. I earned my PhD degree in hydrology and water resources management at UNB in 2017. And after that, I came to the University of Maryland and became a research scientist here. So today I'm going to talk about using hydrological model to assess best management practices in the upper St. John River Basin. And I will also talk about how to develop a decision support tool using field experiments and model simulations. So the title of the presentation is Employing Hydrology Tools to Guide Best Management Practices in the Upper St. John River Basin. So in this talk, I will first introduce the water resources problems as well as the best management practices to address them. Then I will talk about a widely used hydrologic model, the SWAN model, which is used to evaluate best management practices. Next, I would like to talk about developing a decision support system and its application in New Brunswick, and then the conclusion. So as we know that freshwater resources are facing great challenges due to disturbances of human activities and climate change. Rising temperatures are causing more unpredictable weather and extreme weather events, leading to severe floods and droughts. Globally, about 70% of the freshwater is used for agriculture, and non-point salt pollution has been degrading water quality caused by excessive inputs of chemical pollutants and soil erosion. So, to address water resource problems caused by agriculture activities, best management practices are widely promoted and used. These practices can be used to prevent soil erosion, reduce nutrient losses, conserve soil water, and sustain land productivity. However, the questions are when it comes to decision makers and stakeholders, how effective these BMPs are and where they should be implemented in the field. So, in other words, decision makers and stakeholders need data to judge whether they want to adopt certain BMPs. So one way to provide data is through field experiments. We can design and implement field experiments to see how effective the BMPs are. However, we can only conduct limited field experiments because they are expensive and time-consuming. Another problem is that the results derived from experiments are not easily transferable to other study areas, and their results are not validated. And another method is to use physically based distributed hydrologic model to evaluate BMP effects at field or watershed scale. The benefits of using models are obvious. They can fill data gaps of experiments, they can provide accurate results, and they can predict future scenarios. As a result, they are widely received as decision support tools. So here I want to introduce one of the mostly used hydrologic model, SWOT model. The SWOT model is developed by the USDA Agricultural Research Service, and it is designed to simulate water quantity and quality at the watershed scale. The model has been used for assessing impacts of BMPs, land use, and climate change in numerous watersheds across the world. The model can simulate surface runoff, subsurface runoff, and soil water movement. It also simulates soil erosion, sediment transport and deposition, crop growth, and nutrient cycling from soil to water bodies. Point and non-point sources pollutants are also simulated. One of the advantages of using SWOT model is that it has a large database for hundreds of crops and dozens of management practices. This advantage makes it a powerful decision support tool to assess BMPs and land use change at watershed scale. So, I guess this is, this is not the updated PPT. That's fine. Okay, so to create a SWOT project, we can use the ArcSWOT interface as an extension of ArcGIS. The interface requires DEM to delineate the study watershed and create subbasins and river networks. It also needs land use and soil maps to create hydrological response units to simulate landscape processes. HRUs are the basic calculation units of the SWOT model, and together with subbasins, they make SWOT model a distributed model. Water yield and nutrient loadings from HRUs are summarized at the subbasin level, and then the total water flows and the nutrient loadings are routed through river networks. The ArcSWOT interface can be downloaded from the SWOT official website, and it is well documented, and the users can easily set up a SWOT project for a watershed as long as they have all the required input data ready. So, okay, in addition, the model runs at a daily time step with daily weather data input. We can use SWOT model to conduct multiple BMP scenarios in the watershed, and the daily, monthly, annual output can be derived from simulations. And then we can further analyze the effects of BMPs on water quantity and quality at HRU, subbasin, or watershed scales. So let's talk about the application of SWOT in New Brunswick. Basically, we have previously developed SWOT models in two watersheds within the upper St. John River Basin. They are located in the northeastern part of the basin. The Little River watershed is the subbasin of the upper Mississippi River Basin, and the Black Brook watershed is a subbasin of the Little River watershed. So, as the figure shows that there is a nesting relationship between these watersheds. So the Black Brook watershed is located in the province's potato belt. It has been chosen as an experimental watershed since early 1990s, and 9 surface water monitoring stations and 5 weather stations were built in the watershed. Surface water monitoring stations also collect water quality variables, such as total suspended solid, nitrogen, and phosphorus. It has a long-term record of survey data for land management, including, for example, fertilizer rates, fertilization rates, crop rotation, crop yield, tillage application, and the BMP's implementation. The major BMPs in the watershed is flow diversion terrace, FDT, and grassed waterway. So we have utilized the rich dataset of BBW to set up the SWOT model. Water quantity and quality data at the watershed outlet were used to calibrate and validate the model. It is important for SWOT model to account for as much as possible information from land use and management practices, so that model can accurately predict water quantity and quality and evaluate effects of BMPs. So we have developed an algorithm to incorporate detailed survey data from farmland to HRUs in the SWOT model. And as a result, the developed SWOT model can accurately represent annual changes in BMP areas, fertilization rates, and other management information in the Black Brook watershed. These two figures show that SWOT model accurately accounted for annual changes of tillage area and the fertilization rates in the Little Black Brook watershed from 1992 to 2011. In addition, these two figures show the model can account for changes in annual FDT and the grassed waterway areas, as well as spatial distribution of FDT and grassed waterway in the BBW. In other words, the model can accurately mimic BMP changes in both temporal and spatial scales. Overall, these results demonstrated the strong capability of SWOT model for simulation of BMPs at the watershed level. This table shows the parameters adjusted during model calibration for various BMPs, including counter tillage, FDT, and grass water rates. So we had parameter values adjusted to better match simulations of water quantity and quality with observations at outlets from 1992 to 2011. These figures on the right show simulated and observed monthly variations in base flow, discharge, sediment, nitrate, nitrogen, and soluble phosphorus during calibration and validation period. Statistical indices, including R-square and relative error, on the left table indicate that the model performed well for post-calibration and validation period. In addition, distributed models can also provide spatial output with respect to soil erosion and pollutant sources. These two figures show the distribution of average annual soil erosion in the watershed for the calibration and the validation period. We can see that agricultural lands with FDT protection have substantial less sediment yield compared to lands without FDT protection. These results demonstrate the model's capability to detect soil erosion and pollutant sources in the watershed. So let's talk about the decision support tool. As we know that physically based models are not perfect and they have their own problems, especially for decision makers and stakeholders who are not experts in models. For them, physically based model is not flexible and requires complicated procedure and long data processing time. What they need is an easy-to-use tool. So we thought a decision support system which takes advantage of strengths from post-field experiments and hydrological models would be a better option for decision makers. To realize that, we developed a decision support system based on the concept of decision rules, which are used to predict water quantity and quality on a grid cell level. The decision rules can be developed not only based on experiments and model simulations, but also based on expert knowledge. So basically, we first calibrated the SWOT model in the Blackbrook watershed, and then we proceed to conduct multiple BMP scenarios. And the generated simulations at HRUs were used to develop decision rules. As a result, with the help of ArcGIS, we can upscale the results from individual grid to large area to simulate water quantity and quality as affected by BMPs. So before we can use the decision support tool for large basins, we need to evaluate its simulation accuracy. To achieve that, we applied the decision support tool to a larger watershed, the Little River watershed, where we already developed a SWOT model. The Little River watershed, we have two gauging stations monitoring water quantity and quality variables, including stream flow, sediment, nitrogen, and soluble phosphorus. Basically, we compare the model simulations of water quantity and the quality between the decision support tool and two versions of SWOT model. One is calibrated and another one is not calibrated. So I'm not going into details about simulation results. In general, the comparison results show that the model performance of the decision support system in simulations of water quantity and quality were comparable to those of calibrated SWOT at the Little River watershed, and much better than the uncalibrated SWOT. What this means is that the decision support system can, to some extent, replace the SWOT model to predict water resources at larger scales. So for the conclusion, in this talk, I introduced the SWOT model and its application in New Brunswick. Then I talked about how to develop a decision support tool based on field experiments and model simulations to assess the impacts of land use and the BMPs on water quantity and quality for large watersheds in New Brunswick. For future work, we will continue to develop the decision support tool by using machine learning techniques. Furthermore, we will consider more BMPs and include more input data to develop decision rules. An ArcGIS-based interface will also be developed for decision makers to use. That's all I have for today. Thank you for your attention.
Thank you so much. So we're now going to use this opportunity to answer any questions that anyone may have. So feel free to post your questions into the chat, and I will do my best to get through them. We may not get through them, and if you still have a question that you feel compelled to ask, you can certainly send us an email, and we can forward some of those questions either to the presenters themselves or try to find someone who can answer that question best for you. So we have our first question in the chat, and the first question is: can the SWOT model be used to access stream flow response to forest clearing? And that was by Daniel.
Yeah, I can quickly answer this question. Theoretically, I think the SWOT model can do that, but the problem with the SWOT model right now is the forest module. It's not well constructed, or it's not designed for forest management. Fortunately, right now, our group in Maryland has been developing a new forest module. Hopefully, it's based on 3PG. If you know the forest module, it's really popular, and hopefully we can develop the new algorithm in the SWOT model, and at the same time to account for forest management and to simulate, to assess the responses of hydrology to forest management. But right now, at this stage, the SWOT model is not designed for that task. Yeah.
Thank you so much. So just one other quick note. Any other questions that you do have, you can also put down on the feedback form, which will be sent out into the chat in a couple moments here. So if you do have any questions, Tim just put that into the chat right now. You can add those questions onto the feedback form as well. Again, if you have any questions, you can add them right into the chat. Perfect. Thank you, Kim. So how can attendees access the recording of this or the past webinar? What about the written studies, and are they available in French and English? So in terms of the past recordings, if you still have any interest in the past recording, we do have a website. We will put the website link into the chat as well. We'll do that in a couple moments here. We have a web page with UNB that links directly to the YouTube channel that hosts our, Tim just posted into the chat right now, that will host the video of our prior webinar. That prior webinar is a bit more in-depth, featuring two of the presenters we have here today, as well as Dr. Charles Bork, who I believe is on the call as well. And then we also have some other videos on there that give just a broader overview of the Upper St. John Basin as well. So you can access that information through the link that's just been posted into the chat. This webinar here, once everything is completed, it will take us a little bit of time because we do have interpreter services working on the video. So once the interpreters are finished translating the webinar that we're currently participating in, that link will also be posted onto that page as well, and we will certainly let you know when that link is posted. The written studies that these webinars are based on are the ones that we have access to currently are in English. We will confirm if there is one in French. Dr. Charles Bork, one of the lead researchers on this project, is bilingual, so we will confirm if there is a paper that's fully written in French as well, if you need to. And you can send us an email. We can try to sort something out, whether that's more just a quick overview, or if there is a copy that is available, we will get that sorted for you as well. Hopefully that answers your question, Kim.
All right, and yep, thanks again, Kim. And Kim has also pointed out that Tom Slabell had a question above about how to access SWOT and RegCM4, if they're open source, and what languages they're written in, what coding languages they're written in. And awesome. So we could see the source code for SWOT is there as well. But on a more general level, for folks who aren't looking to access the source code, how might government employees, land managers, et cetera, access your programs and put those to use? Dr. Qi, Dr. Shalaby, either of you can take this question.
Shalaby, you want to go ahead? You want to answer the question? Okay. Oh, so I think in order to use SWOT model, we don't need the source code because we can as I mentioned, the SWOT model has a pretty good ArcGIS interface, and you can download it from the website. I just put it in the on the chat, and you can, if people don't familiar with the model, you can try to download it, and if you have the GIS, you can add it as the extension. And the SWOT model itself has a really good documented material, and you can find many examples actually in the package. So you can download it and play with that with several examples within the package, and you can get a sense of that. And but the setup is not really hard. But in order to simulate land management or best managed practices, we need careful designed input data set. As I mentioned in our study, we have a detailed survey data in our Blackbrook watershed. So that's quite important for accurate assessment. SWOT can work if we only have really coarse data set. It will produce outputs, but we should be cautious about the result. And definitely we can use SWOT model to do climate change or land use scenarios, and we can see the responses. But I think the important thing to remember, I think, is the input and how we can incorporate those information from our study area in order to accurately simulate the results. Yeah.
With regard to RxCM, maybe the most difficult things is it is working under Linux or Unix environment. So if the student or the scientist or anyone who are not familiar with Unix or Linux will face this difficulty. But to run the model in Linux, you need a minimum knowledge of Linux, some few commands, and the documentation actually is so detailed to guide the user for all steps toward installation and make the first examples. But also, most of atmospheric models actually have the same problem. Most of them are running under Linux, and they have to be linked to another visualization package. They are not like SWAT. They could be coupled or implemented within ArcGIS framework, so you can create your analysis, create your maps, doing your simulation, all in the same framework. So it would be easy for anyone to create plots and doing their research easily. However, for climate models, I mean, as far as I know, most of climate models or weather models have the same problem. Their packages are separated from the visualization package. So you have to know both. You have to be familiar with both. You might use Python to create your graphs. You might use ArcGIS to create your graphs, because the output files are a general purpose file. So it is easy to be opened by any kind of other visualization, but this will make you jump from Linux environment to Windows environment. It is easier that way. Also, from development point of view, if you would like to develop something within the code, so you have to be familiar with Fortran programming language. Just I want to defend Fortran because there is a misconception. Actually, it is worldwide conception. It is like an extinct language. Not at all. It is very updated and has most features of modern language like C++ and Python. The problem is most of atmospheric models historically are written in Fortran, and this legacy codes, we couldn't just throw it away. We have to reuse it again. So the new Fortrans or updated Fortrans are adapted, and the old code are merged or moved to this new architecture or new programming, new Fortran codes. But Fortran is very powerful, very efficient compared to C++ for many aspects. Yeah. So again, the documentation of RxCM is very detailed, and it could guide you step by step to create your first simulation if you are interested. And I am here anytime, of course. And also the RxCM net is a mailing list. They reply to researcher instantly. So don't hesitate to join this mail list. Thank you.
Thank you so much. So we have another question by Kim. So are there any specific plans for UNB to have courses related to these specific models that are being used? perhaps this is a question that Dr. Bork, who's also on the call, can answer for us.
Yes, thank you for the presentations. I was quite happy to see, especially the presentation relating to the Regime CN4. You certainly provided some insights there. Yes, in terms of courses, we saw this opportunity. The project that we're working on with respect to the upper Wolastoq Basin, we felt that it was a great learning opportunity for our students at UNB. So over the past year, I've been thinking of what to present to the students. There has been some indication of interest in the course that was planned to put in place, and that particular course will probably be aligned very closely with a recent publication that I was involved with and has been published last year. So yes, the intent is to have a course this May, and with the expectation that we will have other courses as we move along on looking at the Wolastoq.
Thank you so much. So the next question in the chat is how such complex tools of assessment, or how can these complex tools of assessment be used in a useful manner in a common household?
I don't understand the question. What do you mean by common household?
Perhaps you can the individual asked question can change the wording, but I'm just gonna try my best to rephrase it. So using the model the models that have been presented in this webinar, on a more broader level, on a more general basis, is there anything that a common household, such as a family or a homeowner that owns property or has their house located by the river, is there anything that they may need to consider and just think about changing in their everyday life going forward when it comes to climate change and possible climate impacts?
Qi, would you like to answer this?
Oh, yeah, okay. Yeah, I think, as I talked about the, decision support system, I think for landowners or stakeholders, or even decision makers, they definitely can have something simpler tools to, to invest, to assess at least, to assess the impacts of climate change or the management practices, land use change. But that's why we are developing this decision support tool. The purpose is to help people to use a simple way to understand the responses of the hydrology and water quality problem to climate change and land use change. And we try to using machine learning or statistic models to simplify our the complex physics. And the basic idea is to select several key variables, and then we develop machine learning models or even regression models. And then we have a predictable result. And use that tool, we can embed it into a ArcGIS interface or other GIS tools. So we can use this tool to help people who don't have an background in hydrology or other related science to just manipulate the and play with this tool and to see the results. And this is one of the objectives of our study, and hopefully we can achieve that. And we are doing that right now, and we have some preliminary results as I showed before. And but we will continue to incorporate more decision rules, or we can call it equations in the decision support tool. And not only for BMPs, maybe we can develop some equations or decision rules using climate model results, right? And we can definitely look at all those variables or intermediate variables and develop some relationships. And those relationships can be tested and to be proved to be reliable. And then we can use that as a estimation tool or decision making tool.
Thank you, Dr. Qi. I'll just say we're actually in the process of developing a key takeaways video. So we do want to make the science and the processes very accessible to anyone in New Brunswick who wants to learn about this science. So we're going to be talking about the study in a more high-level perspective. So it's going to be more broad ideas and relating this so that anyone can fully understand how important this science is. So it'll become more clear how it can be useful for common households after we have that key takeaways video published. It should be published within the next couple of weeks or next few weeks on our website. And we're also planning for another webinar on April 8th, where we will be going over some of these key takeaways as well. So we do want to make this science more accessible so that you don't have to have a background in hydrology to really understand everything. So that's what we're going to be doing in the next few weeks. And also, we do have a highly technical report of this research available in English, and we also have a summary which is still technical in both French and English. So I've put the link again for the feedback form, and there is a question on there which asks which resources you would like us to send to you. So you can fill that in and we'll send that to you very shortly. Also, it's very important that we get feedback on this webinar so that we can continue improving for the next one as well.
All right, we have another question from Dr. Charles Bork, who's also involved in this research. Dr. Shalaby, would you be able to describe the uses of Reg-CM4 specifically in the context of the Wolastoq and that project in the Upper Basin, and describe some of the variables that are of particular importance to this study?
Yeah, thanks, Dr. Charles. Yeah, maybe I would summarize the last study we did for Wolastoq and the impact of clear cutting, of cumulative clear cutting in upper Wolastoq Basin, forest clear cutting, and we design a numerical experiment using Reg-CM4 to see the difference between the surface runoff under the cumulative clear cutting in upper basin. So we have to do two different run as a control run, which is represent the actual or the pristine environment of the upper Wolastoq, and another run that represents or that reflect the cumulative forest clear cut in the upper basin, and to see how this would impact the surface runoff over the basin due to this practice. And we found that as Dr. Charles showed before, that this actually increased the surface runoff, and this would have large impacts in other practices like agriculture and household nearby all the communities nearby the river. It might increase the risk of river Wolastoq spring floods. And so RICCM RICCM tool give us the opportunity to change the land cover or the vegetation cover to do this. And because RICCM is a fully dynamic model, is taking consideration land surface atmosphere interaction, so it realistically represent all physical processes. This was one application, and the second application, which is running right now, to create 100 years of climate projection under two emission scenarios, the extreme one and the lowest one, to see the future of the climate over the whole New Brunswick or maybe most of Atlantic Canada during the 21st century. And for higher resolution, 5-kilometer resolution, and this is not done before, because the available climate change scenarios provided by the federal government is 50 or maybe at most 25-kilometer resolution, and you can see you can see this output on their web page for Climate Atlas. But again, as we show in this lecture, the higher resolution is so crucial to resolve this fine texture, this fine surface texture, like lakes, land, fine topography, and how this would affect for smaller communities along the river. So this is another application. So the main variables, usually it is coming from RICCM, it is depend on your scope. If you are hydrologist, so you are interested in surface variables, surface runoff, snow melt, precipitation, of course, surface temperature, snow cover, and so on. But if you are from other discipline like air pollution, you can looking for surface ozone, aerosols like black carbon who are emitted from forest fire, and other aerosols coming from sea, like sea salt aerosols, and how this would affect other physical processes like cloud formation or maybe health impacts in case of severe air pollution episodes. Also, you might use RICCM for fishery or marine application, like to see the change of sea surface temperature and the impact of change of sea surface temperature with time on many aqua life, like salmon or maybe other kind of marine lives. So that's what I want to say. The applicability of RICCM could be used in many disciplines, not only for atmosphere or hydrology. Thank you.
Excellent. Thank you, Dr. Shalaby. Just a reminder, put your questions in the chat. We do still have some time, so we're happy to take more questions. But in the meantime, I'm going to do a shameless Facebook plug. We are going to be we release the videos that Tim was talking about. We'll be linking the recording both in English and French of this webinar and our previous webinar. We've been sharing the reports, the technical reports we've been talking about through our Facebook. So make sure to give that a follow. If you search at Wolastoq Climate, you can find us on Facebook. I'm sure maybe some of you saw our webinar through that platform, but we will be continually releasing updates through that as well. Fantastic. So let's keep those questions coming if there are any. We're more than happy to put our presenters in the hot seat.
Yeah, I have an idea. Maybe it is a bit crazy about the using RIXM outside research community. Right now, maybe for a long time, farmers start to adopt to use their own weather station. Actually, farmers use weather station in their farm to give them what I kind of call now casting practice. So they're looking for the last 6 hours of temperature or humidity, and they can use their experience to predict the upcoming weather. And of course, this is heavily rely on the farmer experience, which is lasts for maybe 20 or 30 years. But actually, we can use this tool, RIXM, our numerical weather prediction models, to make something called data assimilation. Actually, those weather stations are not utilized within the other weather model that being provided in a public services, like underground weather or Google weather, or this weather doesn't take into account those stations, because those stations are scattered and maybe are related to watershed scale or landscape scale. The global models or the public service weather models rely on what's called official weather station. And those official weather stations are registered in a bigger database. So the farmer can use RIXM and use the actual observation in the last 12 hours or in the last 20 hours to recalculate the forecasts within the framework of the model itself. This would give him or give her a better prediction for the upcoming weather condition. And if he or she could incorporate other weather station nearby farms, so they will have extra accuracy for their prediction, and this would be very, very helpful for them, because as I understand that here in New Brunswick, since the topography is steep in some places, so within 5 kilometer temperature and precipitation would it change largely, maybe 3-degree differences in just in a range of 5 kilometer, and some places would have heavy precipitations and the other farm or the other land does not. So this very localized features could be incorporated and could be predicted. That's what this is the right word. Could be predicted within the framework of using RIXM and localized weather stations. So, yeah. But this needs some kind of special setting within each farm.
I have a question, just more so to engage with participants who may not have a highly technical background in some of this modeling, but are still quite keen on this information. So the question I have is, can you just talk about the importance of upstream processes and their possible effects to what happens downstream, particularly in the lower areas, lower lying geographic areas, and areas that have that are significant to agriculture and have communities in these areas? Can you just speak to that a little bit more? That's a question for either Dr. Qi or Dr. Shalaby. If you guys want to take it together, you're absolutely more than welcome to do that as well.
I don't have too much to say about this topic. It is far from my expertise, actually. So
yeah, okay, I can talk a little bit about that. And I think the the upstream processes is really important, and with respect to the hydrology and water quality perspective. For hydrology, I think for the upstream Junyu River Basin, we have a large portion of forest, and so if the forest changed, like we have, for example, the management and all the climate change effects will change the forest area or the growth, then we definitely have a large impact on the downstream water quantity and quality. And this not only caused floods, also caused a lot of erosions and also nutrient loadings. And I think this is not only hydrology, this is a water quality problem. So the protection of upland area and is quite important. So that's why we have, for most watershed we have, and we have protected the upstream with forest, with strip, with grass waterways, and other practices. And yeah, I think they are quite important. And for the downstream, most of the agriculture lands are located at the flat plant, and they are at the at the downstream area. So the agriculture management of human activities will definitely impact on the water quality. And this is one problem. And another problem people always sometimes they missed is that the upstream protection is another important topic with respect to hydrology and water quality assessment. Yeah. Thank you.
Yeah, maybe I can add a bit more relating to issues of stream temperature. Of course, the more opening that occurs in the upper watershed, that gives opportunity for the water, the surface water, but also subsurface water that would be below the, within the soil itself, that eventually flows and enters into the stream and river system. It's from an earlier study that I did many years ago. It shows that the amount of heating that occurs is proportional to the amount of opening that is occurring in the upper watershed, to the point that the buffers that are normally legislated to be put on the individual streams, large enough to be considered for that, typically the buffers for that particular variable has very limited role because most of the heating occurs upstream including the subsurface water, then, and that eventually reaches the stream, causing the stream to, indicate high temperatures. So that's another element due to, the opening up of the landscape by cutting forests that might lead to increases in temperature of streams, which can potentially lead to problems for cold water fishes that depend on these streams.
All right. Thanks, Max, for the question. Thanks, Dr. Qi and Dr. Borg for those answers. We have a sort of a question in the same vein from Ryan, but more specific to the Wolastoq and to New Brunswick. Ryan wants to know if there are any significant findings or impacts on surface water runoff inside the Wolastoq watershed, especially with the recent increase of conservation forests and P10 legislation. Dr. Borg, if you want to chime in here, I know this is also right in your wheelhouse.
Yes. In terms of the conservation forest and P10 legislation, I can't address that specifically because I don't know very much about that. But what I can say is that from the study that I did over the past year, is that by opening up the headwaters by incorporating more cuts, it does have an impact on the surface runoff, also the subsurface runoff, which ultimately leads into the streams. So the opening up of the forests, especially during the springtime, you get excessive heating of the snowpack, and of course the melting speeds up, and so you get an enormous amount of water entering into the stream and river system, occurring much more quickly than probably if there was a more intact forest cover that would tend to provide shading, and therefore the melting process would be somewhat slowed down. So in fact, we do show that by opening up the forest or the headwaters, by cutting forests, we're seeing a potential for increased flooding with the rate of melting associated with that. And also the frequency of flooding could also increase, given that with climate change, the air masses from the south of New Brunswick are transporting a huge amount of energy and moisture, which contribute to even further in terms of production of snowfall. It's not even, it's not uniform, but there's indication on parts of the upper part of the Wolastoq that the amount of snowfall is increasing due to the flux of humidity from the southern regions of North America towards New Brunswick. So there's, from the studies we've done, there seems to be an indication that we're dealing with things changing quite dramatically. And all of these changes, or some of these changes, can lead to increased water fluxes through the St. John or Wolastoq River. So yes, there's indications of the impact of harvesting on stream flow, and especially also during the springtime with the freshet.
All right, fantastic. Ryan, I hope that answered your question. I'm going to ask one last question, and then I think we're going to wrap up the webinar. So thanks again, everyone, for attending today, and be sure to fill out that feedback form that Tim posted earlier, and we'll be sure to send that out again. Oh. We have one more question from Kim. Is the team willing to have meetings to discuss any special interests with folks who have a special stake in the project? And the answer to that is, of course, please feel free to reach out. So my final question, just sort of as a wrap up of this whole webinar, this whole presentation, is for Dr. Qi and Dr. Shalaby. When you were adapting these tools and getting them ready for this research, what sort of end use did you envision? Is it a tool to inform policy? Are we looking at a national level? Are we looking at using these tools for local landowners, watershed groups? What sort of scale did you design this? Yeah, what sort of scale were you imagining when you were adapting these tools?
Yeah, okay, I will go first. So the decision support system we are developing is actually designed in the first, at the beginning, it's particularly designed for decision makers because we think decision makers has a need for this kind of tool to guide their decision making processes. And we particularly designed it to be easy to use, and it has a very user-friendly interface, and people can just click several buttons and drag some figures within the JS environment. And then people can have the result and the spatial and the temporal extent result. But it's not only it's not limited to decision makers. Actually, hydrologists and other stakeholders, they can also use this tool. This tool can be used not only for small watershed, but also can be used to larger basins like the Upper St. John River Basin. And because we use the decisions, using the decision rule concept and use the ArcGIS, and it works at the grid cell level. So once we have a study area, we can decide the cell resolution, and then we can apply the decision support tool. So I guess there's not much limitation with respect to the spatial area, for the application. And I guess decision makers, stakeholders, hydrologists, they all can use this tool. And basically, it can be applied quite widely across different communities. Thank you.
Yeah, my answer would not differ from Qi answer. Those may be the major groups who are maybe really interested in climate models or hydrological model outcomes. But maybe I'm also interested in persons, just a citizen who may be interested to know by himself the impact of atmosphere or weather on their environment, and their neighbor environment, whether he's an individual farmer, whether he is a fisherman, but actually sometimes public weather information or atmospheric information is not so useful, but maybe people, citizen or normal people, they should have or should learn how to interpret maps. Maybe this is a real difficulties. Maps are usually interpreted by experts, hydrologists, meteorologists, who knows how to read maps. Maybe we need to find a way to translate or to teach people how to read maps, or even we can invent a method to to make this map readable by others. Maps is very useful to give bigger picture information, not only localized or town information. Maybe I'm keep thinking about this. I don't know if this would answer your question, Linus, but really this would be could transform the science itself, because if people are participating in criticizing or have a feedback on this kind of information, this would have large impact on research itself.
Excellent. Yeah, that absolutely answers my question. And that's all we have time for today. So again, thank you so much, Dr. Shalaby, Dr. Qi. Those were some amazing presentations, and we're excited to see where you take your research and how it develops. We're really happy to be involved. And thank you again to everyone who attended today. It's great to see so much interest in this research. And yes, please fill out our feedback form and stay tuned for our next webinar and those videos as we release them. So thanks again.
Thank you.
Thank you.
You all.
Bye-bye.
Bye-bye.
Bye.
Thank you all.